In this video, we're going to analyze an LC circuit and do our analysis in the S domain. My objective in this video is to try to provide you with some vital insights about S domain analysis. The advantage of this approach is that we don't need to formulate our solution in terms of differential equations, and this method also expedites the computation because the initial conditions are included into the circuit in the S domain. In the S domain, capacitors and inductors are treated as if they were just resistors, and therefore we can directly apply Ohm's law and other circuit analysis techniques that we know to solve the equivalent circuit in the S domain. And then instead of applying calculus, we can just solve the circuit algebraically. And then after finding the solution, we can then apply the inverse Laplace transform to obtain the final solution in the time domain. Before solving the circuit in problem 1 shown here on the screen, let us first take a look at the model circuit's derivation for the resistor, inductor, and capacitor in the S domain. Okay, let's go ahead and see how we can do it. Okay, let's start with the resistor. So we have a resistor, and the resistance of our resistor is R. The current flowing through the resistor is I, and the voltage across it is V. And then by Ohm's law, we have V equals IR. Now if we take the Laplace of both sides, we have the Laplace transform of the voltage is equal to, now this resistance is just a constant term, so we can just put it at the front. So we have R times the Laplace transform of the current, and therefore we have V of S equals R I of S. This is now the relationship between the voltage, current, and resistance in the S domain. And then we can translate this equation into a circuit like this. So the resistance is still R, but now the current is I of S, and the voltage across the resistor is V of S. And this is now the circuit model for the resistor in the S domain. Okay, next is the inductor. So we have an inductor, and the inductance of the inductor is L. The current flowing through the inductor is I, and the voltage across it is V. We know that the voltage across the inductor is given by the following equation. V equals L di over dt. The derivative of the current with respect to time is simply the rate of change of the current flowing through the inductor with respect to time. And if the current flowing through the inductor is not changing, then di over dt is 0. And if this di over dt is 0, then L times 0 equals 0, implying that V, the voltage across the inductor, is 0. So in other words, if the current flowing through the inductor is not changing, then the voltage across the inductor is 0. Although some current flows through the inductor, as long as it is not changing, then the voltage across the inductor is 0. This is how we interpret the equation. Okay, let us proceed with our derivation of the circuit model of the inductor in the S domain. The voltage across the inductor is given by the following equation. V equals L di over dt. If we take the Laplace of both sides, we have L multiplied by the Laplace transform of di over dt. Okay, so V of S equals L. Now the Laplace transform of di over dt is simply S I of S I0 minus. Okay, then by simplifying the right hand side, we get L S I of S minus Li 0 minus. Okay, now we have an equation for the inductor in the S domain. Okay, we are going to translate this equation into its equivalent circuit. So we have V of S here, and then the inductor is here in series with this voltage source with this particular polarity. The current flowing through the circuit is I of S. The inductance of the inductor in the S domain is L or Ls, and which is the term here. And this voltage source is this term here, Li 0 minus, and I0 minus is the current flowing through the inductor at time t equals 0 minus, and this is the initial condition of the inductor incorporated into the circuit in the S domain. So this equation and this circuit are equivalent. If we apply KVL and solve this circuit, we can derive this equation. So this equation and this circuit are equivalent. Okay, so this is the series circuit model of the inductor in the S domain, and now we are going to find its parallel model by manipulating this equation and solving for I of S. So I of S equals V of S over SL plus Li 0 minus over SL. Now the inductance in the numerator and the denominator cancel out, so I of S equals V of S over SL plus I0 minus over S. Now we can translate this equation into a circuit, and the equation says that I of S splits into two branch currents. So the current through the inductor and the current source. So if we have a circuit like this, we have a circuit with two branches, and let's say this is the inductor here, and this is the current source pointing downward. So the inductor has an impedance of SL, and the current source is having this magnitude I0 minus over S. So the voltage across this terminal is of course V of S. So this current I of S splits into two after reaching this junction. So the current through the inductor is V of S over SL, which is this term. So as we can say, the inductor is across is parallel to the voltage source V of S. So the current flowing through the inductor is this term, V of S, the voltage across the inductor, divided by the impedance of the inductor is L. And we have the current source here with a magnitude of I0 minus over S. Now I0 minus is still the same. This is the current flowing through the inductor at time t equals 0 minus. And this is the initial condition of the inductor incorporated in the circuit in the S domain. So this circuit is derived from this equation, and they are equivalent. Okay, so now we have two models to choose from. We have the series model and the parallel model for the inductor in the S domain. Okay, let's continue with our derivation. And now we're going to derive the circuit model for the capacitor in the S domain. Okay, for example, this is our capacitor with a capacitance C. Let's say the voltage across the capacitor is V. Then the charge in the capacitor is equal to CV. So, for example, if the capacitance in the capacitor is 1 farad and the voltage across the capacitor is 1 volt, then the charge in the capacitor is equal to 1 farad times 1 volt is 1 coulomb. Okay, so what is the meaning of a charge of 1 coulomb? So a single electron is equal to, or the single electron has a charge of 1.60219 times 10 to the negative 19 coulombs. So in other words, a coulomb of charge consists of the following number of electrons. So 1 electron over 1.60219 times 10 to the negative 19, and this is equal to 6.24 times 10 to the 18 electrons. So this is 6 quintillion 240 quadrillion electrons. So what is the meaning of this data? Okay, so if this is our capacitor, this is the positive plate and this is the negative plate. The positive plate, although it is positively charged, it still contains some electrons. Let's say the number of electrons in the positive plate is in plus, and the number of electrons in the negative plate is in minus. Then, in order for the capacitor to have a charge of 1 coulomb, then the following relationship must be true. So n minus is equal to n plus plus 6.24 times 10 to the 18 electrons. So in other words, in order for the capacitor to have a charge of 1 coulomb, then the negative plate must contain a number of electrons that is greater than the number of electrons in the positive plate by 6.24 times 10 to the 18 electrons. If we have a capacitor with a capacitance C and let V be the instantaneous voltage across the capacitor, and Q the instantaneous charge of the capacitor, then Q equals CV. And then differentiating both sides of the equation with respect to time, then dq by dt equals C dV by dt. Okay, the derivative of the charge of the capacitor with respect to time is the current flowing through the capacitor. So it is equal to I, and it is equal to C times the derivative of the voltage across the capacitor with respect to time. and taking the Laplace of both sides, we get the Laplace transform of I is equal to C multiplied by the Laplace transform of the derivative of the voltage with respect to time. Okay, so I of S equals C multiplied by, now the derivative of dV by dt is equal to S V of S minus V0 minus. Okay, simplifying the right hand side of the equation, we get CS V of S minus C V0 minus. Okay, now this term here is a current source, and this one is the current flowing through the capacitor. So since the right hand side of the equation contains two terms, so our circuit must contain two branches. So if this is the current source and this is our capacitor, then our V of S is here, and we have I of S here. Now the magnitude of the current source is C V0 minus. Now this V0 minus is the voltage across the capacitor at time t equals 0 minus, and this is the initial condition of the capacitor included in the circuit. So now it's time for us to calculate the impedance of the capacitor. Now the impedance is simply voltage over current. So the voltage across the capacitor is V of S. So this is our capacitor, and it is connected in parallel with V of S. Therefore, the voltage across it is V of S. And the current flowing through the capacitor is this term here. So C is V of S. Now V of S in the numerator and the denominator cancel out, leaving us with 1 over Cs. And this is the impedance of the capacitor in the S domain. So now we have successfully derived the parallel circuit model of the capacitor in the S domain. Okay, the current source must be pointing upward because of the sign. So in order to satisfy this equation, this current source must be flowing into the node if this I if this I of S is flowing also into the node, and then the current flowing through the capacitor must be flowing away from the node. Okay, so now it's time for us to derive the series circuit model of the capacitor by computing or solving for V of S in this equation. Okay, so if we solve V of S, we get V of S equals I of S over Cs plus C V0 minus over Cs, and the C and C cancel out, so we get V of S equals I of S over Cs plus V0 minus over S. Okay, so this is a voltage source, and this one is the voltage across the capacitor. So if this is our V of S, and this is I of S, So our capacitor is here, and a voltage source is in series with the capacitor with this polarity. Okay, so the magnitude of the voltage source is VO minus over S. The impedance of the capacitor is 1 over CS. And now we have derived the series circuit model for the capacitor in this domain. So this term here, V0 minus, again, this is the voltage across the capacitor at time t equals 0 minus, and this is the initial condition incorporated in the circuit. So now we have two models to choose from for the capacitor in the S domain. We have the parallel circuit model, and we have the series circuit model. Okay, so now we have just equipped ourselves with essential tools required to analyze an RLC circuit. So let's get back to problem number 1 and get ourselves ready to solve it. Okay, this is the problem number 1. So as shown in figure 1, this is figure 1. The capacitor is connected to the source voltage via a single pole double throw switch. If the circuit has been in this state for a long time, find the voltage V of t across the capacitor after the switch is flipped into terminal 1 from terminal 2 as shown in figure 2. Okay, so the problem states that the capacitor in figure 1 here has been in this connection for a long time. So it means that the capacitor has been fully charged, and if the capacitor is fully charged, then there is no more current flowing through the capacitor, and in that condition the voltage across R2 will be equal to 10 volts, which is the source voltage here, divided by R1 plus R2 times R2. If we plug in the values, we get VR2 equals 5 volts. Since R2 and the capacitor are connected in parallel, so it means that the voltage across the capacitor when it is fully charged is also 5 volts, and this is our V0 minus. Okay, before proceeding further, we need to clarify first some notations. Okay, what is meant by V0 minus, V0 plus, I0 minus, and I0 plus? Okay, now V0 minus is the initial condition for the capacitor, and I0 minus is the initial condition for the inductor. Now the initial condition for the capacitor is in the form of voltage, whereas for the inductor it is in the form of current. Okay, so what is V0 minus? V0 minus is the voltage across the capacitor at the instant before some event happens, and in this case the event is the flipping of the switch. So it means that V0 minus is the voltage across the capacitor at the instant before the switch is flipped, and V0 plus is the voltage across the capacitor at the instant after the switch is flipped. So in the same way, I0 minus is the current flowing through the inductor at the instant before the switch is flipped, and I0 plus is the current flowing through the inductor at the instant after the switch is flipped. Now, since the voltage across the capacitor cannot change instantaneously, therefore we can say that V0 minus is equal to V0 plus. So in the same manner, I0 minus is equal to I0 plus, because the current through the inductor cannot change instantaneously as well. So I think we have clearly understood this concept. Okay, now we're going to find the initial condition of the inductor. And for the capacitor, we have already found its initial condition, and it's V0 minus, and it is equal to 5 volts. Now for the inductor, looking at this circuit here in figure 1, initially the inductor is not connected to anything, and therefore the current flowing through the inductor at time t equals 0 minus is 0. So I0 minus equals 0. Okay, now after flipping the switch, the circuit in figure 1 will then look like the circuit here in figure 2. And the circuit that we are interested in is this portion. And this is the circuit that we are going to analyze. Okay, this is the circuit that we are going to analyze. We have a capacitor, and the capacitor is in parallel with the inductor, and the capacitance of the capacitor is C, the inductance of the inductor is L, and this is the voltage V of t across the capacitor and the inductor that we are going to calculate after flipping the switch. Okay, this circuit is still in the time domain, and therefore we need to rewrite this circuit into its equivalent configuration in the S domain. And we can do it by using the models we previously derived. Okay, before converting this circuit from the time domain to the S domain, let's take a look again at the circuit models that we derived a while ago, so we can explain what will happen to the circuit models when the initial conditions are 0. Okay, here are the models we derived a while ago. This is the circuit of the capacitor in the time domain, and this is the parallel circuit model and the series circuit model of the capacitor in the S domain. Okay, if the initial condition of the capacitor is 0, then V0 minus equals 0, and C times 0 equals 0, which means that the current source is 0. Now, if the current source is 0, the current source will behave as an open circuit, and this parallel circuit model will reduce to this form. Okay, in the same way, for the series circuit model, if V0 minus, which is the initial condition of the capacitor, is 0, so 0 over S equals 0. And if this is 0, it means that the source, the voltage source is 0. And if the voltage source is 0, it will act as a short circuit. So the series circuit model will also reduce to this form. Okay, now let's go to the inductor. Okay, this is the inductor circuit in the time domain, and this is its parallel model and its series model circuit in the S domain. Okay, if the initial condition of the inductor is 0, it means that I0 minus equals 0. So 0 divided by S equals 0. It means that this current source is 0. So if the current source is 0, it will act, or it will behave as an open circuit, and this circuit will reduce to this form. Okay, in the series model, if I0 minus equals 0, then L times 0 equals 0, and this voltage source is 0, and if the voltage source is 0, it will behave as a short circuit, and therefore this series model circuit of the inductor will also reduce to this form. Okay, I think we are now in a position to rewrite this circuit into its equivalent form in the S domain. Okay, let's copy this circuit and paste it here. Okay, so we are going to apply the parallel circuit model of the capacitor in the S domain. Okay, so this is our circuit in the S domain. This is our V of S, and this is the capacitor, and this is the current source pointing upward. The impedance of the capacitor is 1 over Cs, and the current source is CV0 minus, and this thing here is the parallel circuit model of the capacitor in the S domain, and this is our inductor. The impedance of the inductor is L. Now the inductance did not change its form because its initial condition is 0. Okay, we can now apply KCL to solve the circuit. Now this current source splits into two currents. So the first one is IL of S, which is the current flowing through the inductor, and the other one is IC of S, which is the current flowing into the capacitor. Okay, now we are going to write the KCL equation. So CV0 minus equals IC of S plus IL of S. So CV0 minus equals the current through the capacitor is equal to the voltage across the capacitor over its impedance 1 over Cs, and the current flowing into the inductor is the voltage across the inductor divided by its impedance is L. Now CV0 minus equals, if we simplify this term here, we get Cs V of S plus V of S over is L. Now multiplying both sides of the equation by SL, we get LCS V0 minus equals LC S squared V of S plus V of S. Solving for V of S, we get LCS V0 minus over LC S squared plus 1. Okay, now dividing numerator and denominator by LC, we get V of S equals S V0 minus over S squared plus 1 over LC. Okay, now we know that the Laplace transform of cosine 80 is equal to the integral from 0 to infinity of a to the negative st cosine 80 dt, and this is equal to s over s squared plus s squared. Now in this equation, our a squared is this term, so a squared equals 1 over LC, and therefore a equals the square root of 1 over LC, and then we can rewrite a squared as the square root of 1 over LC squared. Okay, now rewriting this equation, we have V of S equals V0 minus multiplied by S over S squared plus the square root of 1 over LC squared. Okay, now I can now apply this formula here into this equation. Okay, now let's take the inverse Laplace transform on both sides. We have the inverse Laplace transform of V of S is equal to V0 minus multiplied by the inverse Laplace transform of S over S squared plus S squared, and we need to put the bracket here. Okay, so the inverse Laplace transform of V of S is simply V of t, and V0 minus, and the inverse Laplace transform of this expression here is simply equal to cosine square root of 1 over LC t, and this is the equation for the voltage across the capacitor and inductor after flipping the switch. Now I think our solution is quite interesting, because the cosine function here suddenly appeared out of nowhere, and the mathematics predicted the oscillating voltage. Now our voltage V of t is oscillating because of this cosine function here, and because there is no parameter that can attenuate this expression here on the right hand side of the equation, we don't have any resistance to attenuate the signal. It means that this voltage V of t will continue to oscillate forever. Okay, accidentally I committed some errors in writing the equation. Let's fix them first. Okay, here instead of writing E squared, I should have written the square of the square root of 1 over LC. And here I forgot to write the capacitance C. Okay, it's done. Okay, this term here, the square root of 1 over LC, is also known as omega naught, and its unit is radian per second. It is also known as the circular or the radial frequency. Now W omega naught and the frequency are not equal. Okay, frequency, the unit of frequency is cycle per second, which is equal to hertz. Okay, now to find the relationship between omega naught and frequency, we need to ask the following question. Okay, how long will it take for omega naught to travel an angular displacement of 2 pi? So in other words, we need to multiply omega naught by time, which is t. Now, since 2 pi is the displacement, the angular displacement for a single period, then we can replace this small t with capital T to represent the period, and then we need to multiply it by omega naught. Now, since t is the period, it means that it is the reciprocal of frequency. So omega naught multiplied by 1 over f equals 2 pi, and therefore we can say that omega naught is equal to 2 pi f. Okay, so this is how we derive the relationship between omega naught and frequency. Okay, so we can rewrite this equation. V of t equals v0 minus cosine omega naught t. Now, our v sub v0 minus equals 5 volts, and omega naught is equal to the square root of 1 over LC. Now, our inductor's inductance is 1/20th of a Henry, and the capacitor's capacitance is 1/10 of a farad. Therefore, our omega naught is equal to the square root of 1 over 1 over 20 multiplied by 1 over 10, and therefore our omega naught is equal to the square root of 200, which is equal to 14.14, and the unit is radian per second. Okay, so let's calculate the frequency. Omega naught is equal to 2 pi f, and therefore our f is equal to omega naught over 2 pi, which is equal to the square root of 200 over 2 pi, and we have 2.251 hertz. Okay, and the period is 1 over f, 1 over 2.251, and this is equal to 0.44 seconds. Now we can plug in the values into the equation. So we get V of t equals 5 volts cosine 14.14 t. And if we graph this equation, it will look like this. Okay, so the amplitude is here, this is 5 volts, and then the period is here from this point to this point, this is one period, and as we can see, this is 0.44 seconds, and then the frequency of this is 2.251 hertz, and because there is no resistance in the circuit, this V of t will continue to oscillate forever. Okay, we are going to compare our calculation with the simulator. We are going to simulate this equation in Electronics Workbench. Okay, this is the circuit that we have just solved, and we are going to simulate this circuit using the Electronics Workbench to see how the circuit responds when the capacitor gets connected to the inductor after flipping the switch. Okay, let's start the simulation. This is our simulator, the Electronics Workbench, and I have already wired the circuit here, and as we can see, the capacitor is still connected to the source voltage via R1 and R2, and I have also installed a voltmeter across the capacitor to monitor its voltage. And as we can see, the voltage across the capacitor is 5 volts, which agrees with our calculation for the V0 minus. And we have also an oscilloscope, so we can see the waveform of the voltage across the capacitor and inductor. And this is the switch. Now let's flip the switch. Okay, we noticed that the waveform started at 5 volts at time equals 0, and that is correct because we have a cosine function in our equation. Okay, let's measure the amplitude of the waveform. We are using channel A of the oscilloscope to monitor the waveform, and our setting here for channel A is 5 volt per division, and the amplitude of our waveform covers 1 division. So 1 division times 5 volts per division is 5 volts. So the amplitude of the waveform is 5 volts. And we can also notice that the amplitude of the signal does not seem to have any attenuation, and it is due to the absence of any resistance in the circuit. Therefore, the voltage will continue to oscillate indefinitely. Okay, let us also measure the period of the signal. The period starts here from this point to this point. Okay, the number of divisions that the period covers is 1, 2, 0.2, so 2.2 divisions. And our setting here for the time base is 0.2 seconds per division. So 0.2 seconds per division times 2.2 divisions is 0.44 seconds, and this figure also agrees with our previous calculation. Okay, so we have seen that the simulation result and our calculation are totally in agreement. Okay, so that's all for today, and let's stop here for now. But we are going to continue our topic in the next video by analyzing another circuit consisting of a resistor, a capacitor, and an inductor. Okay, thank you for watching.